Hey guys, welcome once more to our YouTube channel. It's always a pleasure to have you. Today we are having a video series on Littoral Mock 2023, the very first episode. Make sure you stick around to check every concept that we're going to be explaining today. We're not in a rush for anything in the world. We're digging in. Littoral mocks are very crucial. You should know that by now. And so, yeah, let's have all the time to go up in every concept that was there in that mark. Let's go. So, guys, this is our video outline. So, today we're going to be looking at episode 1, which is basically question 1 to 13 of Littoral Mock. Let's go. Yeah, guys, thank you so much for always checking out our channel. We are so grateful. We're sending out smiles and hugs to all those who are huge admirers of our work. Make sure you subscribe, turn out the notification bell so that you don't miss any other uploads from our channel. Also, please help us share our content to other A-level students and to your friends. Engage yourself very much with the content. If you are learning alongside us, make sure you get a piece of paper, a book, and a pen so that you're solving and calculating and getting your answers before you play the video to check out what we have done. Thank you so much. Let's go. The relationship between four physical quantities given by P minus Q minus RS equals 0. Really, given that the equation is homogeneous, which of the following statements must be correct? Well, before we look at those statements, we have to understand that, well, a homogeneous equation is one with every added term having identical units, okay? The next part I want you to realize from this definition is that, well, P is an added term to Q, which is an added term to RS. Therefore, P, Q, and RS have identical units, okay? So we have to go through the answers and see which one gives us this answer. Boom, that's the answer. So it says, D says the product RS must have the same units and constants. Okay, and constants, that's not true, okay? Because homogeneity simply tells you that, well, every added term has the same base unit, not necessarily the same constants, all right? So this guy is off. The product RS has the same units as P and Q. Correct. P, Q, R, and S all have the same units. Not true. Because R and S here might be two different physical quantities. But when you multiply them together, they give you a single term. And that term is added to Q, added to P, so they have the same base units. But these physical quantities that multiply together don't have the same units, not necessarily, okay? The unit less constant in Q minus RS is equal to that of P. Not necessarily. Again, homogeneity is not about their constants, it's about their unit. So C here is our best answer. Which list of quantities contains only scalar quantities? Well, mass, acceleration is off. Mass, volume, electric potential, kinetic energy. Correct. B is correct. C says acceleration, it's off. D says moment, it is off, it's vector. So B is our answer. Two ball bearings X and Y are projected from a horizontal ground at the same time. X has a mass 2m and is projected vertically upwards with speed u. Y has mass m and is projected at 30 degrees to the horizontal with speed 2u. Neglecting air resistance, which statement is correct? Okay, let's just do some work here, right? So this is our first drawing, that's for y. So you're projecting it at speed 2u at an angle 30 degrees from the horizontal. So you have this velocity time graph. We can get the initial vertical component of this velocity, right? So we have to resolve this 2u in the vertical direction. That will give us 2u sine 30, okay? Horizontally, I've not resolved the horizontal component well because, well, there are good reasons for that. We'll talk about them. Well, if you draw the velocity time graph for the particle that is thrown upwards vertically, that's x, you realize that when you throw it upward, it decelerates to rest, right? This is the speed time graph, really. And then at this particular point, this maximum height, it begins to fall back downwards, and then the speed increases, right, before it strikes the ground here. Okay, so those are the speed time graphs for both particles. Now if you get over here, their initial momenta, so the initial momentum of x is of course 2mu, but in which direction? In the vertical direction, because x is initially thrown upwards with a velocity of 2u, okay? Its mass is m, so the velocity of u, its mass is 2m, so we multiply those two together, you have 2mu vertically. Now for y, you are projecting it 30 degrees from the horizontal. So what that means is you are going to get this mass multiplied by its initial velocity, so you get its initial momentum as 2mu2, but momentum is a vector quantity, so you have to take into consideration the direction. All right, this guy for x is vertically upward, for y it is 30 degrees from the horizontal, so it's not vertically upward, so they have different directions, hence these two momenta are not equal. All right, because momentum is a vector, it takes into consideration the magnitude. Yes, we have the same magnitude, but we don't have the same direction, so we are not equal. Okay, so time to reach maximum height, that's what we saying here. But how do you get time to reach maximum height for projectiles? You have u sine theta over g. Okay, so u sine theta is of course vertical component of velocity, right? Or you just say that, well, theta here for this guy who is projected vertically upwards for x, you realize that our theta will be 90, so you put sine 90, you have sine 90, which is 1, so you basically have u over g. That's your time to reach maximum height. For y, you're going to have u sine theta, but what is your u? The initial velocity for y, the initial velocity of y is 2u. Sine 30 there is half divided by g, so you have u on g again. It means that these two particles take the same time to reach the maximum height, so they reach maximum height at the same time. So x and y each reach their maximum height at different times. B is not true because they reach at the same time. So if they reach their maximum height at the same time, it means that their time of flight will be equal. All right, because time of flight is 2 times time to reach maximum height, which makes D correct. X and y reach the ground at the same time, so D is correct already. But let's say y c is wrong. The maximum height reached by y is half that reached by x. Okay, let's show that. Maximum height, of course, is u over g. Okay, no, uy squared over 2g, that is initial vertical component of velocity squared divided by 2g. For x, initial vertical velocity will just be u squared divided by 2g, so you have this. For y, get this guy here, this is our initial vertical velocity, 2u sine 30, which gives you u squared out over 2g, so you realize that they have the same maximum height, u squared over 2g, u squared over 2g. So yeah, they are equal right there. So C says the maximum height reached by y is half, which is not true, right? Because they reach the same maximum height. And so our answer here is D. A pellet with velocity 200 meters per second and mass 5 grams is fired vertically upwards into a stationary block of mass 95 grams. The pellet remains in the block. The impact causes the block to move vertically upwards. What is maximum velocity, vertical displacement of the block? Okay, this is a collision between the pellet and the block. We have to apply the conservation of momentum first. Okay, so from law of conservation of momentum, initial momentum of the system, which is basically that of the pellet because the block is initially at rest, right? So this guy is 0. Initial momentum of this guy is 0. Initial momentum of the pellet is mass of pellet, initial velocity of the pellet equals. Now when they strike, they stick together. So because they stick together, we're going to have mp plus mb here, which is the mass of pellet plus mass of the block, multiplied by the common velocity which they move upwards. Okay, so you realize that we can make v common the subject here, and that is it. When you make it a subject, you key in these figures, right? So each time you have these problems, please pause, try to solve them your own way before I continue. So we have v common there to be 10 meters per second. Now, from law of conservation of energy, you realize that, well, initially the system had just kinetic energy because the pellet was the only one moving. But after the pellet strikes the block, right? So immediately the pellet strikes the block, the whole system has just kinetic energy. But the system now begins to rise. They begin to move upwards like this. So all of that kinetic energy is being converted to gravitational potential energy as the system rises in a gravitational field. So we are going to calculate how much height you're going to rise through simply using this principle of conservation of energy between the various types of mechanical energy of the system. So K is lost to PE, so you put that in equation and then you make H the subject, you have that, you key in the values, you have 5.1 meters, and our answer is steel ball is released from rest at a distance above a rigid horizontal surface and bounces several times. The diagram in figure 1 shows how its velocity varies with time. No. Which statement correctly explains why the areas x and y are equal? Okay, so we have a velocity time graph. Of course we have to recognize that the area under a velocity time graph gives you the displacement covered, all right, or the distance in that particular direction. But well, I'm just giving some points for you to note here. So note that the area under a velocity time graph signifies displacement or distance in a certain direction the particle covers. Okay. X describes the position when the particle is rising. Guys, just come back here a little bit. So it released from rest. So you release it from a height, right? Initial velocity is 0, and then it falls towards the ground. The velocity is increasing as falling towards the ground because it's accelerated by acceleration due to gravity, right? And so at this particular point where the velocity peaks is just when the particle is about to strike the ground, the first impact. Now when the particle strikes the ground, velocity is a vector quantity. It has to bounce off and then move in the opposite direction, because moving in the opposite direction, the velocity has to take into consideration that, all right, now the velocity has also changed direction. So you realize that the velocity is now negative. Okay, so you quickly drop here and then you get negative. Now it begins to rise all the way to 0. This is now maximum height. Now maximum height, the particle now reverses. It begins to fall back towards the ground. And so when it's falling back towards the ground, you realize that it has reversed, so the velocity is now positive. Okay, so it's accelerated by acceleration due to gravity towards the ground, and just before it peaks, or just before it strikes the ground, this is where it peaks. Boom, you get a second impact there. So you understand the dynamics of the motion right here, right? So from X all the way to this point, this is when the particle is rising from the first impact. And then from this point all the way to this point is when the particle has risen to its maximum height and then reverses. It's now falling back down towards the ground. So of course you expect that the distance it covers when it rises to maximum height is equal to the distance it covers when it reverses at that maximum height and then gets back to the ground, right? So those distances are equal. That means that these areas like this have to be equal. Okay, and that's the significance of these areas being equal. All right, that they cover equal distances at the ball is rising to its maximum height, and when it reverses and starts falling back towards the ground. And that answer clearly is D. The ball rises and falls through the same distance between impacts. Correct. Now, let's look at what we're saying here. X describes the portion when the particle is rising after the first impact. Correct. And Y describes the portion the particle is falling towards the ground to make its second impact. Correct. Okay. Now, if area X equals area Y, then the particle covers same distance when rising as when falling. Okay. This implies the experiment takes place in the absence of drag forces of any kind. Of course, because if there are drag forces, then you realize that the particle might do a lot more work against frictional forces, maybe on its way up, all right, than on its way down. So these areas will not quite be the same. Okay, so but let's just say why these other answers are wrong. The ball's acceleration is the same during its upward and downward motion. Not true. Acceleration is a vector quantity. So when the particle is falling downwards, it's being accelerated. When it's going upwards, it's being decelerated. And those two accelerations have opposite signs. So not true. B says the speed at which the ball leaves the surface after an impact is equal to the speed at which it returns to the surface for the next impact. Yes, we are neglecting air resistance. This statement is very true, but this is the problem. The problem here is that it does not explain why these two areas are equal. Okay, yeah, so if you're neglecting air resistance, then this is true, but this does not explain why these two areas are equal. All right, for one impact, the speed at which the ball hits the surface equals the speed at which it leaves the surface. That's not true, or at least we cannot say that from the graph, but from mathematics and from our understanding of collisions, right? It's not possible for a collision in real life to be elastic. Okay, that's when the coefficient of restitution between the ball and the ground is equal to 1. That's not possible. So you realize that, well, it's on the basis of that C is wrong. Yeah, so D is our answer here. A small water drop leaves a tap with 0 velocity at intervals of 0.2 seconds. They then fall freely 0.8 meters to reach a horizontal surface. How far has the drop fallen when the previous drop hits the surface? Please pause the video and try solving it. All right, let's go. Oh, I've displayed the answer already, so the answer is B. All right, so let's show that the answer is B. For the previous drop, that's the first drop that is just hitting the ground. Now, what distance has it covered? It has covered all the distance from the tap, from where the droplets of water are dropping, to when they are hitting the horizontal floor surface. Okay, So that distance is 0.8 meters. It's a vertical distance, so I'm calling it y. U is 0. Okay. Acceleration, of course, they are being accelerated by acceleration due to gravity. So we're going to use equation of motion y equals ut plus half at squared, and we're going to notice that, well, u is 0, so we can make t the subject. It is 2y over g. You notice that, well, our t is going to be that. Take square root, t 0.4 seconds. Now the succeeding droplet has been falling for what? 0.4 minus 0.2 seconds. Why? Because when the first droplet fell off, for the second droplet to fall, it has to delay by 0.2 seconds. So it means that it has to allow this guy to fall for 0.2 seconds first before it dropped off. So if I have the total time for which this guy covers, then the total time for the succeeding guy after it to drop would simply be 0.4 seconds minus that 0.2 seconds that guy delayed to come out of the tap. All right. So hence, for the succeeding drop, we can now use y equals half gt squared, because u again is 0. Then our y would simply be half g. Our t is what? It has been falling for exactly 0.2 seconds when you take this difference. And so that is 0.2 meters. And that our answer is B. The given diagram in figure 2 illustrates a projectile launched at point O following the OPQRS. Air resistance may be neglected when the projectile is at the highest point of its path. Which of the following statement is true? Okay. So you clearly have this. The horizontal component of the projectile's velocity is 0. That's not true. Okay. Horizontal component of the projectile's velocity is always constant. It does not change. Why? Because gravity does not act in the horizontal direction. Alright. The horizontal component of the projectile's acceleration is 0. True, because gravity. What is a projectile? A projectile is the motion, or the motion described by a particle which is given an initial impulse and then allowed to move under the influence of gravity alone. All right. So gravity acts only downwards, vertically downwards. So there's no component of gravity horizontally. So that's why the particle has no acceleration in the horizontal direction. B is correct. The kinetic energy of the particle is 0. So here, the kinetic energy of the particle cannot be 0. Why? Because, well, the particle here has a horizontal component of velocity. I've said that throughout this part. O, P, Q, R, S. The horizontal component of velocity is always u cos theta. That is not changing. So even at this point, it has not changed. Okay. In fact, at this point, the particle has 0 vertical velocity, but the same horizontal velocity that is started off with at O. Okay. So yeah, that gives you the kinetic energy in the horizontal direction. The momentum of the projectile is 0. That's not true. But the vertical momentum will be 0. The horizontal momentum is still the mass of the particle multiplied by the component of velocity in that direction, which is u cos theta. Okay. So yeah, this is not true. So our answer there is B. A uniform metal rule of weight 2 newtons is freely pivoted at 70 centimeter mark. The system holds the metal rule in a horizontal position and suspends 5 newton weight from the 100 centimeter mark. Okay, so this is our diagram. We could just get another diagram down here that shows us a lot of things. So yeah, this is where the weight acts from. Don't forget about the weight of the metal rule. So it acts at the center of the metal rule. That's 50 centimeters from one edge. So if this is 70 centimeters, right, because these people that are 30 centimeter mark from this other edge, or the 70 centimeter mark from this end. So you notice that, well, this guy, the distance from this weight all the way to this pivot must be 20 centimeters, right? So we can put that there. This weight is going to be turning it anti-clockwise, so we make that anti-clockwise moment to be positive. So 5 times 0.3, because the distance here is 0.3. And then minus, why is it minus? Because this is now an opposite moment to this. This is a clockwise moment. Oh, is this a clockwise? No, this is anti-clockwise. This guy is clockwise now. Yeah, this guy is clockwise. This guy is clockwise. And then this guy is anti-clockwise. Okay, so you notice that they are opposite moments, so that's why there's a negative there. And then the result is 1.1 Newton meter in the anti-clockwise direction. Well, but we just need the magnitude here. So the answer is 1.1, and the answer is C. Narrow beam of monochromatic light is incident normally to a diffraction grating. The first order diffracted beam makes an angle of 20 degrees with the normal of the grating. What is the highest order visible with this grating at this wavelength? Okay, this is interesting. D sin theta equals m lambda. That's our normal routine diffraction grating equation. So for the first order image, m is 1, theta is 20 degrees. So we'll put d sine theta here equals lambda. Now, but m max would simply be d over lambda. Why am I calling this m max? Well, because to get m max, sine theta here has to become maximum, right? And sine theta is maximum at 1. So you notice that you simply have d over lambda here to get maximum order. So we simply reciprocate sine 20. We're going to get d over lambda, right? So get 1 over sine 20 from this equation 1 will be equal to d over lambda. So what does that tell you? It tells you that whenever you reciprocate the sine of the angle that a particular order image makes with the central order, you get the maximum possible orders on that diffraction gradient. So you just have to reciprocate this like that. You get the maximum possible order. So that gives you 2.9. So which makes it 2, because you never round up diffraction orders. Okay, never rounding them up. This is very close to 3, but the result is 2. So the only two orders are possible on that diffraction gradient. So our answer is A. A long rope is fixed at one end while the other end is moved up and down, resulting in a stationary wave as shown in figure 4. Which of the following is the phase difference between the oscillations at x and y? Okay, notice that x and y are within one loop, alright? So they are contained between two adjacent nodes. This is a node, this is the next node. So because these two particles are contained within two adjacent nodes, then they are in phase. The phase difference between them is just 0. But I've given some key points here for you to take note of. Point 1. Phase of all the particles in between two nodes, so in between two nodes like this, is always the same. So these particles are always in phase. But particles of two adjacent nodes differ in phase by 180 degrees. So if I get a particle here and I get another particle here, they differ in phase by 180 degrees. Okay, yes, particles at nodes are permanently at rest. I think you should know this. Statement 3 says the amplitude of vibration changes from particle to particle. Right, the amplitude is 0 for all at nodes and maximum at the antinodes. So you have 0 here at the nodes, and then it's rising all the way till you get to the antinodes. So it's maximum, the amplitude of oscillation here. Okay, so that's the amplitude of vibration is what varies within one loop, but not their phases. Within one loop, their phase is just equal, right? Except for the particles at the nodes, which differ by 180. Okay, so our answer here is B. A particle has a kinetic energy Ek and a de Broglie's wavelength of lambda. What is the Broglie wavelength when the particle has a kinetic energy of 4 Ek? Alright, this is easy. Ooh, I've displayed the answer already. Okay, lambda is h over p. That's the Broglie's equation. Okay, so the wavelength is related to the momentum of the particle by, lambda equals Planck's constant divided by the momentum. Now, of course, you notice that momentum is, of course, mass times velocity. But if I square that, I'm going to write mass squared, velocity squared, right? I'm squaring both sides of the equation. If I divide all through by 2m, I'm going to get, divide all through by 2m here, you'll get p squared over 2m. Divide all through by 2m here, you would have one of these m goes one of them. So you have half mv squared, which gives me kinetic energy. So this tells me that, well, momentum will be equal to what? Kinetic energy Ek multiplied by 2m, then square root of that. That's why you have 2m, kinetic energy square root. So what's my momentum? Get this now, place it back in here. Our wavelength now becomes, well, h over the momentum, which is 2m Ek. So what does this tell me? It tells me that there's a relationship between wavelength and kinetic energy. So if the kinetic energy increases, the wavelength decreases. Why? Because they're inversely related. So if it increases by a factor of 4, this guy should reduce by a factor of what? By a factor of root 4, which is basically 2. That's why wavelength reduces. The new wavelength now is lambda 2. Okay, good. So our answer is A. Which phenomenon cannot be explained by the wave theory? Well, look at this. What are some of the properties of waves? Well, they can be diffracted, they can undergo interference, they can undergo polarization. So the only guy that is not a consequence of the wave theory here is C, which is a photoelectric emission. Okay, so our answer here is C. The diagram below shows 4 energy levels of an atom drawn to scale. These energy levels give rise to a part of an emission spectrum. Which pattern of lines will be obtained from these energy levels? Okay, there's an error with the diagram, right? Because the closer you get to infinity, the closer these energy level lines appear to be. All right, so you notice that this guy is rather farther from this guy than this guy is from this guy, which is totally messed up. All right. So let's just solve a question that came in London GCE 2001. Okay. So yeah, this is a very similar problem, but I want to show you how reasoning behind this question can really help you solve the Littoral Mock problem. So we're still going to solve that one, but let's look at this one. The scale drawing shows 5 energy levels of an atom. 5 possible transitions between the levels are indicated. Each transition produces a function of definite energy and frequency. Which spectrum corresponds most closely to the transition shown? All right, so they've given you particular transitions. Okay, so you notice that they've not given you any transition between E5 and E4. All right, so now they've given you the transition between E5 to E1 and the rest. Now, but this is increasing frequency. You know that the guy who is going to be at the extreme here is going to be the guy with the biggest energy difference. Okay, and the guy with the biggest energy difference, of course, E5 to E1. So that is going to correspond to the largest frequency here. So this right here is that guy, or this, or this, or this. Now the next that is going to closely follow it, because these energy levels appear to converge, so this guy is closely going to follow this guy. So E4 to E1 is going to give you an energy difference that is very closely associated to the frequency of this guy. So that's why you see very closely follows. Now, but now you get E3 to E1. Notice that there's this gap like that. The gap E5 to E4, and then the gap E4 to E3. There's that gap between these two. So the energy difference now will be slightly higher, slightly lower. All right, which means that the frequency will correspondingly be slightly lower. And so you notice how this is closer, and then this guy is a little bit farther from them. But now when you're done with this guy, when you go over to get the energy transition from E5 to E2, look at how tiny this line is. Okay, so that tells you that each energy difference is not as huge compared to these other guys. So what's going to happen? You're going to get a huge fall in the frequency of the associated waves that are produced by these electronic transitions. So that's why you leap from here all the way down here, because this transition now is so small, so the frequency that's associated there is very small, and then followed by this guy, which is again very small, so you get this guy. So B obviously is the answer here if you follow through the transitions. All right, so you get the point now. Now if we go over to the right question, you notice that hey, this guy has to be closer instead to this guy, and so we could get this drawn like this, and then I start representing these energy transitions. So this first one, right, because you are talking about increasing wavelength, so the guy over here should be the guy with the longest wavelength, which corresponds to the guy with the shortest energy difference, okay, or the guy with the shortest frequency. So this is that the guy right here. So that's the first guy. Now the next guy is going to be this guy right here, okay, but the gap here is slightly bigger, so you notice that you get a very short wavelength, and then you have this leap. Now if you go next, you have this guy, because these two lines appear to converge, so they are a lot closer. So this guy is a lot closer to this next guy, even though I've not still drawn it to scale. So you notice that these two guys are closer. So far B, A and B are on track. Now if we go next to the next energy transition, you have this leap. There's this leap, right? So, and you now have to move from here all the way down. I think this B is slightly on track too. D and C were off a long time ago. Oh no, D is still on track. Now if you notice, we have now this energy leap, so we're down here, right? We're down here. Now the next would be this guy. Now notice that it would be close to this guy but not so close, so you get this guy here, and then the next would now be this guy. So there are 6 transitions that are possible, so you get over here. So A obviously is the answer, but these guys, B is not the answer, because look at these guys are just equally spaced, telling you that the energy transitions are equally spaced, which is not possible for an atom. Okay, yeah, so our answer here is A. Thank you guys so much for watching the video to the end. Thank you who are sticklers to our channel. We appreciate you, appreciate the love. Please make sure you stay tuned for the other parts of the video. Leave your feelings down in the comment section below if you enjoyed the video. Thank you so much. Keep subscribing if you're not yet subscribed. Hit the bell so you don't miss any updates from our channel. See you next time.